vector space is a set with two operations, one called sum, the other called multiplication by scalars. A sum takes two vectors of a vector space and gives back another vector. Multiplication by scalar takes one scalar, takes one vector, and gives back another vector. Now, in this video, we are trying to show what happens when we take two vectors in a vector space whose objects we can draw, and sum these two vectors up. We have seen in the previous video that in the case of R squared, the vector space given by the Cartesian product of R times itself, that vector space can actually be drawn. All the elements can be associated to points in a plane with a coordinate system, a two-dimensional coordinate system like the one we have depicted here in this picture. Therefore, it makes sense to wonder what happens when we start from the point associated to the vector AB, the point associated to the vector DE, which are being denoted with the yellow dot and cyan dot respectively. What happens when we sum them up in the vector space and we associate the geometrical point to the sum? Okay, so algebraically we know that the sum of these two vectors is going to be a vector in R squared given by these two coordinates. The first coordinate is the sum of the first two coordinates of the vectors of the summons. Therefore, it's going to be a plus d according to the notation we have introduced. And the second coefficient of the sum will be, again, the sum of the second coefficients of the summons. Therefore, the vector will be a plus d, comma, b plus e. Now, if you draw them, let's assume that d and a are exactly as shown here on the picture. Then a plus d will be a real number, exactly in this position. Likewise, b plus e will be exactly here if we assume that e is here and b is there. This implies that the point associated to the vector sum of the two, is going to be precisely this red dot right in this place. Okay, this does not give much information on the geometrical relationship that lies between the cyan dot, the yellow dot, and the red dot. So let's first consider an animation in which we are changing the vectors, the summons, yellow and cyan, and consequently we see how the sum of these two vectors changes. Okay, let's see. I have introduced the coordinates of these points. In this case, we are assuming that the cyan dot has first coordinate 2, second coordinate 3. Then consequently, the vector sum of these two will have a first coordinate 6 and second coordinate 4. Now let's change and move these two yellow dot and cyan dot and see what happens to the sum of these two vectors. Okay, so as you see, again, there is not much geometrical insight except that at each instance in time we will have that the first coefficient of the sum vector will be the sum of these two first coefficients and the second one also. You are encouraged to stop this animation at any time and to check that up to an approximation of like 100, this is exactly what happens. Now, let's go a little bit more into detail in the geometric construction. Now we will see that indeed they don't really move. These 3 points, they move accordingly to certain geometrical rules that are quite explicit in these constructions we are going to make. So we are going to show that actually the red dot can be found without knowing explicitly the coordinates of these 2 points, of the summons. As long as we have 2 points in the plane, we can actually geometrically construct their sum by means of the following. We connect the origin to the yellow point through a line. We translate this line in order to make it pass through the cyan point. At that moment, we know that the sum of these 2 points is going to lie on this translated line. We don't know exactly which point it will be representing the sum, but we do know that the sum will actually lie on that translated line. In order to find exactly what's the point that is going to be the sum of these 2 vectors, we have to repeat the same construction with respect this time to the cyan point. Therefore, we'll draw a line through the origin and the cyan point, and then translate this line up to the yellow dot. Now the line of before and this new one will intersect, and the intersection point will be exactly the sum of these 2 vectors. Let's see. You see, we translate up to that point, and then we translate the other line up to this point, and we see that, as I anticipated, the point associated to the sum of the 2 vectors is precisely the intersection point of these 2 translated lines. From this picture, we also notice that the points representing the summons and the point representing the sum of the 2 vectors, they actually are vertices of a parallelogram if we take as other vertex the origin. Okay, so origin, 2 summons, and the sum will always stay on a parallelogram. So here we have highlighted the parallelogram bounded by these 4 vertices. Same constructions can be achieved by replacing lines with arrows. The concept is the same. We translate the arrows from one summon to the other summon, and we will notice that these arrows, they have a common ending point, which is precisely the sum of the 2 vectors. Let's see now the animations we've seen before, but with the geometrical construction that represented the sum of the vectors through the arrows. So the last ones that we have performed. So we see again that at each instance in time we will have a parallelogram whose sides are precisely this arrow and their translated ones. Okay, at each given time, you see here, 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 there is always a parallelogram that is being formed by these arrows, or equivalently has vertices, the origin, the 2 summons, and the sum.